The acids and bases section of the chemistry paper starts with question 1.7, which reads, reactions 1 and 2 below have equilibrium constants Kc greater than 1. And then we are given two reactions here that are reversible reactions between acids and bases, where Kc is greater than 1, which means that the concentration of our products is always going to be far greater than the concentration of our reactant. And so the question reads, based on the reactions above, the acids in order of increasing strength are. And we start here by identifying the acids and conjugate acids in each reaction, where we can see that in reaction number 1, H3X has donated a proton to HCO3, which makes this an acid. And as a result, that makes HCO3 our base, which then in the reversible reaction makes H2CO3 our conjugate acid for this base, and H2X is then our conjugate base, where H2CO3 would donate a proton to H2X. In reaction number 2, we see that the hydronium ion is the one that donates the proton to H2X, and that makes our hydronium ion the acid, the H2X the base, and H3X is then our conjugate acid in the reversible reaction, where it can now donate a proton to H2O, which makes H2O our conjugate base. So what we can see here is that there are now three acids that we are looking at, those being H3X, H3O+, and H2CO3, where the reactions or the acids in the forward reactions are generally considered to be stronger than the reversible reactions because we've been told that our Kc value is greater than 1, which says that these acids tend to ionize completely, which would tell us then that the strongest acid is either going to be H3X or H2CO3. And the way that we decide which one of those is stronger is by realizing that H3X is not only an acid, but is also a conjugate acid. And since it's an acid and a conjugate acid in two different reactions, that means that neither of them is going to be particularly strong, which would then suggest to us that H3O+ is going to be our strongest acid. Our H3X is going to be the second strongest acid because it still is an acid in a forward reaction with a Kc value greater than 1. And then our weakest acid is going to be H2CO3, which only appears as a conjugate acid. So in order of increasing strength from weakest to strongest, that would mean that H2CO3 is our weakest acid, H3X is our second strongest, and H3O is then our strongest acid. And that means that the correct answer here is option B. Question 7 reads, sulfuric acid is a strong acid present in acid rain. It ionizes in 2 steps as follows. And 7.1.1, define an acid in terms of the Bronsted-Lowry theory. And Bronsted-Lowry defines acids and bases in terms of their proton behavior. And so we say that an acid in the Bronsted-Lowry theory is a proton donor. In the Bronsted-Lowry theory, an acid is a proton donor. Question 7.1.2, we are asked, write down the formula of the conjugate base of H3O+. And when we are asked a question in this way, what they are telling us is that H3O+ is an acid. By asking for the conjugate base, they mean that this thing is an acid. And so we want to know what the conjugate base is, and we find the conjugate base by giving away a proton from that compound. And H3O, when it has lost the proton, becomes H2O. So the question reveals to us, by them asking us for a conjugate base, they are telling us that this substance is an acid. And so we find the conjugate base by donating or giving away a proton. Question 7.1.3 asks, write down the formula of the substance that acts as an amphiolite in the ionization of sulfuric acid. Now, this question is tricky because there are two substances here that we know act as ampholytes under certain situations, the one being HSO4, the other being H2O. But this question specifies it must be an ampholyte in the ionization of sulfuric acid, meaning in this process that we see up here, it must act as both an acid and a base. And we can see that in this process, in the reverse reaction of reaction number 1, HSO4 acts as a base when it accepts a proton from H3O+. So in this case, it is a base. And in the second reaction, in the forward reaction, HSO4 acts as an acid when it donates a proton to water. So what we see is that in this scenario above here, HSO4 minus is the only substance that acts as both an acid and a base, where although there is water present and water can act as an ampholyte, it does not do that in this reaction above here. So the correct answer to 7.1.3 is HSO4 minus. Question 7.2 reads, acid rain does not cause damage to lakes that have rocks containing limestone or calcium carbonate. Hydrolysis of calcium carbonate results in the formation of ions which neutralize the acid. Question 7.2.1 asks, define the hydrolysis of a salt, and the correct definition for hydrolysis is the reaction of a salt with water. Hydrolysis is the reaction of a salt with water. Question 7.2.2 asks us to explain, with the aid of the relevant hydrolysis reaction, how limestone can neutralize an acid. And what we need to see here is that when limestone is placed in water, it would immediately dissociate, meaning that there are two ions that are present in water, those ions being the calcium ion and also then the carbonate ion, both the ions present in limestone. What we can immediately see is that the reaction between calcium and water is not possible because calcium does not have a proton. It does not have a hydrogen ion that it can donate to water. And since calcium is positively charged, it is not going to be able to accept a hydrogen ion from water. So there is no reaction or no hydrolysis of calcium with water. Whereas on the other hand, the carbonate ion is able to attract a hydrogen ion from the water molecule or accept a hydrogen ion from the water molecule, which would turn that into hydrogen carbonate, HCO3, with the valency of -1, and leave us with some hydroxide ions. So since the calcium does not react with the water, it is not necessary to show that reaction or non-reaction in the answer. The only reaction that is required is to show that the hydrolysis between carbonate ions and water forms hydroxide ions. We have not fully answered the question here because they ask us to explain this with the aid of a diagram. And so we're just going to say, since there is hydroxide, that is going to neutralize with the acid. The question has asked us why limestone is able to neutralize an acid, and it's because when there's limestone, there's hydroxide, and hydroxide is able to neutralize with any acid that is present. Question 7.3 reads, the water in a certain lake has a pH of 5. 7.3.1, calculate the concentration of the hydronium ions in the water. And so we would always start with an equation that is given in the formula sheet, that equation being that for pH, pH is equal to the negative log of the hydronium ion concentration, where the pH has been given to us as 5, and that is once again the negative log of our hydronium ion concentration. And so we can therefore say that our hydronium ion concentration is equal to 1 times 10 to the power of -5, and it is a concentration, so that is moles per cubic decimeter. This was calculated by saying that the hydronium ion concentration is equal to 10 to the power of the negative pH, but this formula is not given in the formula sheet and so cannot be used as such. Question then goes on. The volume of water in the lake is 4 times 10 to the 9 cubic decimeters. Lime or calcium oxide is added to the water to neutralize the acid according to the following reaction. 7.3.2. If the final amount of hydronium ions is 1.26 times 10 to the 3 moles, calculate the mass of the lime that was added to the lake. And so what we have here is we have already calculated the concentration of the hydronium ions in this water in the lake. We have then been told what the volume of water in the lake is, which allows us to immediately say, well, if we know the concentration and the volume of water in this lake, we can then calculate the initial number of moles of hydronium in this lake. And we can do that using the formula concentration is equal to the number of moles over the volume, where our concentration has been calculated in the previous question, 1 times 10 to the negative 5. The number of moles is unknown, and the volume we've been given as 4 times 10 to the 9 cubic decimeters, which then tells us that the number of moles of hydronium that are present in this lake initially is equal to 4 times 10 to the power of 4 moles. The reason why this is useful is because if we know the initial number of moles in the lake, we can compare that to the final number of moles which has been given to us in this lake. And we can therefore calculate the number of moles of hydronium that reacted. So the number of moles of hydronium that reacted is then simply going to be the initial number of moles minus the final number of moles. The initial number of moles we've just calculated as 4 times 10 to the power of 4. The final number of moles was given to us as 1.26 times 10 to the power of 3, which then tells us that the number of moles present, or the number of moles that reacted, is 3.8740 or 38,740 or 3.874 moles. The reason why this is useful to us is because now that we know how many moles of hydronium reacted, we can use the balanced equation to find out how much calcium oxide it must have reacted with. We do this by showing that we know the ratio of hydronium to calcium oxide in this balanced equation is a ratio of 2 to 1, which means that if we use 38,740 moles of hydroxide, we would have required half of that in calcium oxide, that being 19,370 moles of calcium oxide. And then we can finally get to answering the question, where the question has asked us to calculate the mass of the lime that was present in the lake. And so we can say that our number of moles is equal to the mass divided by the molar mass, where the number of moles we've just calculated as 19370, and that is equal to the unknown mass over the molar mass of calcium oxide, which is 56. And therefore, our mass of calcium oxide that is produced is then 1084720 grams, or we could write this as 1.08 times 10 to the 6 grams. Important to see here that in this question, I have not rounded any of my answers, where in the marking guidelines, the answer was rounded here, which would have resulted in a different answer at this point, which would have resulted in a different final answer of 1.09 times 10 to the power of 6 grams. And although these answers are slightly different, you would not be penalized for either one of these, although I would recommend that you get into the habit of only rounding the final answer in a question to 2 decimal places. A question like this, marked according to the guidelines, question 7.1.1 is a definition straight from the guideline document, and therefore 2 marks for proton donor. Question 7.1.2, the formula for the conjugate base is H2O. You have been asked for the formula. and not the name of that compound, and so it is H2O, the formula. Question 7.1.3 was for 2 marks, correctly HSO4, minus again asking for the formula specifically. Question 7.2.1, the definition for hydrolysis is also 2 marks for the reaction of a salt with water as per the guideline document, although the reaction of cations or anions with water was also accepted, but this reaction is this definition here is the more correct definition for hydrolysis of a salt. Question 7.2.2, explain with the aid of the relevant hydrolysis reaction how the limestone can neutralize the acid. There were 2 marks allocated for the correct reaction, showing the reaction between water and carbonate, and then 1 mark for the explanation showing that you understand that since there is hydroxide present, that would neutralize with the acid. Question 7.3.1, there's 1 mark for writing down the correct formula. There's 1 mark for correct substitution and 1 mark for the correct answer, provided that the correct units are given for that value. Question 7.3.2, being quite a long question, there are a number of options that are available. The first mark is allocated for calculating the number of moles of acid that is initially present. So there's 1 mark for using a formula and 1 mark for the correct substitution. You are advised to use this kind of notation where it's very clear that this is the number of moles of hydronium that is initially present. It makes it easier for the marker to see what you have done. There are then 2 marks for a calculation showing or calculating the number of moles that reacted. Once you know the initial amount and you've been given the final amount, there's 2 marks for calculating the number of moles that reacted. Once we know that number of moles that was reacted, we were allocated 1 mark for using the ratio to find the number of moles of calcium oxide that were present. And then the last mark was allocated for correctly converting the number of moles of calcium oxide into a number of grams using the relevant formula, and then 1 mark for the final answer using the correct units. Again, the rounding is important here, although both were accepted, you are encouraged to only round the final answer.